Okay. Let's get into it here. Do you have one? 2.1? You do have one? Thumbs up. I do not have it. The universal symbol for no. All right. So skydiver. We did one. We did one on number one on whatever the day it was, Friday. Now, so skydiver problem would be, now this is one of the rare problems where we have to take air resistance into account, because if there was no air resistance, if you went skydiving on the moon, for example, your force diagram would be very simple at all times. You guys know what it would look like? That's what there would just be one force. Yeah, so if you were on the moon, this is all you'd have is mg. And so you would accelerate and accelerate and accelerate, and you would just keep accelerating until you hit the surface. But if there's air, so if you're wondering what's happening with air resistances, generally speaking, I mean, it's very complex, but the general principle is like, there's all these molecules, and these molecules have mass. And so it's like when you run into, if you run into something in real life, it slows you down, right? Well, air has mass. It's like, you run into it slowed me down. Same thing with air. I mean, you run into these air particles, these molecules, and there's a bunch of different ways you can think about it. Like, they're absorbing your energy, or there's collisions going on. But in the most general sense, the air has mass, and so when you run into it, it can slow you down. Okay, just like anything else. So anyway, so what we're going to do is account for that. So the skydiver has just jumped from the plane and is traveling downwards, speeding up. The operant word here, words, are speeding up. Okay, so now so the goal here with this stuff is to get your think in terms of diagrams and force diagrams. So if you're speeding up in this direction, I guess we can make it, instead of a little square, we can make it a little man, I guess, or a woman, whatever. There's a skydiver just above the plane. This vector is mg. That's the force due to gravity. What kind of arrow is going to be pointing up? Big or small? Small. So yeah, I mean, anytime you're moving through air, there's going to be a little bit of air resistance. But if you just jump out of the plane, he's not going that fast. And so the force from the air is not going to be that big. And so look at this diagram. What direction is the net force pointing? Down. And so the question says, find the direction of the net force. So we might maybe over to the side say, just make some indication. The F net points down. Okay. Now, if your F net points down, what's your acceleration doing? Yeah, it's negative. It's making you go more fast, more down. That's why you're speeding up, right? So if your net force points this way, that's the direction that your acceleration vector points, which means if you're already going this way, then you're speeding up. Conversely, if you were heading this way and your net force is pointing down, you'd be slowing down. How does that last statement? Does that make sense? So just long story short, your acceleration always points in the same direction as your net force. So that was part A. Part B, the skydiver has reached terminal velocity. Ooh, what's that? Does anyone here know what terminal velocity is? The fastest you can go. The fastest you can go in air. So bit of a trick question, I guess. What is terminal velocity on Earth?
Or is it different for different stuff?
Yes. The answer, like a lot of things in science and stuff, is it depends. So the terminal velocity for, these scissors is not the same as the terminal velocity for a feather. Yeah. Like a bowling ball, you drop the bowling ball, that thing can go really, really fast in the air before it hits terminal velocity versus, like a piece of paper. So that stuff is extremely complicated. You can take not only an entire class, but you can do an entire PhD in fluid dynamics and there's actually still a big unsolved problem in fluid dynamics about how, like, when something's traveling through a fluid like air, what actually is happening on like a small scale. But anyway, like modeling that accurately is very difficult. So anyway, you guys ever seen that? Like, there's a couple of famous videos where like they talk about you can take like a candle, right? You put out a candle so a little bit of smoke's coming out of it in like a totally still room. And even like the most advanced supercomputers cannot fully predict exactly how that smoke is going to like travel upward and kind of billow and spiral and stuff. It's just too complicated. So it's an example of a chaotic system. Okay, so sorry. You got this doesn't change, right? This is mg. When you hit terminal velocity, that means so think about this. Even if you never heard of it, you can still reason it out. I'm telling you that means that you have hit a point where you're not speeding up anymore. You've hit your max speed. So what's your net force then? 0. Very good. 0. Think about that. Make sure that makes sense to you. If you're not slowing down or speeding up, right? If you're traveling at constant velocity, then your net force must be 0. So let's write that down. So if you're traveling at constant this arrow actually goes both ways. If the net force on the system is 0, then it's not speeding up or slowing down. And then conversely, if it's not speeding up or slowing down, then the net force must be 0. So we know that if you're wondering what's happening here, well, the faster you go, if you've ever put your hand out the window in a car, or like skied or done anything where you're moving fast through air, then the faster you go, the more you feel that air, right? So the faster you're going, the bigger this vector grows and grows and grows and grows, but eventually it becomes the same size. Does that make sense? So here's part B. This is the guy reaching terminal velocity. Hello.
Hey, can I see Trent?
Certainly. So no questions on this one? Good sense. Okay, so part C is asking, he just deployed his parachute and is rapidly slowing down.
Yes.
Okay, there's his parachute. Again, like if you want to get into the details of this, think about what I mentioned at the beginning about those air particles, air molecules. So when I'm falling, my body hits a bunch of air molecules, right? And those slow me down because they have mass. Well, what happens when I open up a parachute? You're hitting a lot more air molecules each moment. So you're expanding that surface area. So you're going to hit a lot more. Also, the shape of it tends to get you extra force too. If you don't want it to be flipped the other way. Anyway, so I still have the same mg, same exact gravity force, but now what's this vector going to be doing? Big force. If you've never skydived, I'm assuming most people have skydived before. I haven't, but in a car, if you slam on the brakes, this is what you're feeling. So if you're in the car, it's often very confusing to people. You're in a car, right? Let's say I'm going this way, I'm driving. You slam on the brakes, right? What direction is the net force on you? Backward. A lot of people go, but I get shot forward, right? I slam on the brakes, my body goes forward. Well, that's because your body's moving through space, and so is the car. When you hit the brakes, the car is the first thing to slow down. Your body lunges forward. So what prevents you from flying out of the car? Well, the seatbelt or the windshield, I guess. Exerts a huge force on you this way that slows you down. Okay, so like in this case, what he's going to feel, he's traveling down. He's going to feel this like huge lurching forward sensation, but really what's happening is the harness is pulling him very strongly upward. Okay, so does that make sense? We're all good with that? Okay, so then part D is he's at terminal velocity again. So if you're picturing this process, he hit terminal velocity, right? And then he deploys the parachute, and now still got the parachute.
Doesn't look like a parachute.
It's a pretty good parachute. Come on. This also can be a little confusing. This diagram is pretty much identical to which, other than me drawing a little parachute on him, it's identical to which one?
The one without the parachute.
This one. Yeah, so then someone might raise the objection, wait a second, how can it be the identical force diagram? He's going way slower here, right?
Yeah.
Okay, that's the whole point of a parachute. Is that you go slower with the parachute deployed. So what's going on? Well, he's changed his geometry, so now his terminal velocity is much lower, but it's still equal and opposite forces. Gravity still pulls down on him with the same amount of force. It's just that now you get this big air force without having to go very fast. That's the idea of a parachute. Now it requires less speed to generate this much upward force. Okay, so he just hit the ground. There's another one. Who here's ever jumped? If you've ever jumped, you'll know that when you land, you feel something, right? What? That's a good drawing. Everyone's a critic, my goodness. So, Caleb. Okay. The gravity force is still mg. Does Earth care that you just jumped? No, he doesn't know anything. He just knows that you have a certain amount of mass. Earth is sitting there. He's like, I got all this mass. I'm Earth. You've got some mass. Yes, massive. Is that even a pun? That's literally what the word means. That's literally what the word massive means. Yes, it has mass. Or as my professor once said, this is like one of my, I don't know why this sticks out in my memory so much, but one time he's this guy that, he had a very strange accent. I eventually figured out what kind of accent it was, but I always thought he was Russian. Turns out he was Mexican, but I swear. And he was holding some kind of object, whatever, it could be a marker. And he just goes, he's trying to explain some principle, and he goes, it waits. You see? It waits. I'm thinking like, what do you mean? What's it waiting for? Well, what he meant was it has mass, like it has weight. So anyway, it waits. Interesting way of phrasing it. No, I swear he had like an Eastern European sounding accent. For the whole time, I'm like, is he Russian or is he like Ukrainian or something? No, he was Mexican the whole time. He was from Mexico. Anyway, Orozco. I guess his name could have been a clue to me. His name was Orozco. Anyway, so when you jump, right? So when I land on the ground, you'll feel, oh man, that ground is like pushing up big time on you to slow you down. You can illustrate this again, like. Now it's the force from the ground. You can illustrate this by jumping on, I don't know, like a not very thick plank of wood or something. If you jump on it, at a certain point, the wood can't produce enough upward force and it snaps, right? So when you land on the ground, after jumping or falling or whatever, the ground exerts this huge force on you. This is why if you fall from a really great height, you can get a big boo-boo, because if you're traveling really fast and you hit the ground, then this vector is huge. The ground is exerting a massive force on you for a very short period of time, and that gives you the boo-boo. You don't want that. Okay, now he's safely on the ground. He's chilling. Here he is. He's no longer squatting, Caleb. There you go, happy. He's just standing there, so now it's gravity again is mg. The force from the ground is equal and opposite. So maybe there's a lot of stuff to think about here, but one thing, for example, is, does Earth ever exert a different force on you? No. Maybe if you lose or gain weight or something, yeah, that would change. If you lose mass or gain mass, then this number changes. Or we'll find later, if you move really far away from Earth, like really far away, you can actually, this number decreases. But the ground can exert a lot of force on you, or not that much, or the ground is kind of can produce a variable amount of force. Okay, so why don't you guys try answer number 3 on your own. See if you can get it's a little bit of a tricky question, but hopefully you guys get it. You love cannons, Colin. And then we're gonna get into some calculation. That'll be great.
Is this with air resistance or no?
No air resistance.
No.
Good question. Never account for air resistance unless the question explicitly says it, because it's like, yeah, because that can make a lot of confusion, right? That would it would affect any problem we do pretty much. So I'll let you know for sure if we need to account for air resistance. I don't think there's any more on this problem set where we need to think about it. Don't fall for the what the ancient Greeks used to think, impetus. There is no impetus. It's not real. And keep in mind, it is a force diagram, not a diagram of like velocity vectors. All right, hopefully you got all of them. I'm gonna put all mine in one diagram. Here's the cannon. If you're still working, you're probably overthinking it, which is okay. We haven't been doing this very long. Here's the path, right? If I were to draw the velocity vectors, how would they point? Someone give me one really good word that starts with a T that would just describe what do all the velocity vectors look like in respect to this path? Huh?
Tangent?
Yes, they'd all be tangential. So if I was drawing all the velocity vectors, they'd look like this. Pew, pew, pew. Right? Those are the velocity vectors. But the force vectors look like, okay, let's say it's on its way up. How many forces are acting on that guy right there? 1. Ignore air resistance. If you really want to include air resistance, it points tangentially opposite to the velocity vector. If you're wondering about that, but we're ignoring air resistance. There's just gravity. Who else can be pushing on him right now? Remember the impetus idea is wrong. So there's no force required to have something be in motion. Was there a force required to get it in motion, like in the cannon's barrel?
Yeah.
Sure, yeah. There was, if we drew the cannon, here's the cannon. Here's some more extra stuff for you if you're curious. Here's the cannonball inside the barrel. You know what happens, right? In like a gun or a rifle or a cannon is there's some matter in there that undergoes a chemical reaction, like an explosion. It expands very rapidly, heats up greatly. When it heats up and it expands, like all that gas wants to go. He's like, bruh, feels like there's like a ton of pressure in here. There's not much pressure out there, is there? So I want to get out. It exerts a huge force on the cannonball. So what happens in this barrel is there's a massive amount of force over a very short period of time. But once it leaves the barrel, it's a projectile. So this whole time he is a projectile. If you're a projectile, then nothing is acting on you other than gravity. It's the same vector the whole way. Classic physics question. Yeah, it's a classic question of, I'm going to give you some extra information, the capital T, they like to go, a 4 kilogram projectile was launched out at a 62-degree angle from this height, and it has been traveling for 2.7 seconds. What's the net force on the projectile? The answer is just mg. Make sense? So in that made up example I just told you, you would just make a vector pointing straight down. That was 4 times 9.8 would be the answer. So summarize the 3 diagrams in one sentence. Well, for a projectile, right, the net force points straight down, and it's just the force from gravity. Or you can phrase that more concisely if you want. How are we feeling about this? Does this make sense? Okay, we're almost getting into the calculation ones, which maybe will be more fun. You're on a frictionless ice rink, and you slide a puck across the ice with an initial speed of 20 meters per second. Draw a force diagram for the puck 2 seconds after it's released, and find the puck's net force and acceleration. Think about that one. This is it's not our last chance, but hopefully we're in the process of wiping out any simple misconceptions about how things are working here. So who thinks they know the answer to this question with confidence? Is it what?
Is it none?
That's very close. The net force is 0. The acceleration is 0. Let's discuss why that is the case. But now the only thing I would disagree with you is I wouldn't say there's no forces. There's going to be 2 forces here. So here's the puck. Yeah. So this is the fun part, or maybe not fun, but this is the part that I think is really nice and I don't know, I guess pleasing about physics is you can think about it in just little small increments and then it all makes sense. So okay, let's put yourself in perspective of the puck. He's been sliding for 2 seconds, right? So he's clearly away from the guy. Let's go to the most basic thing. What is a force being exerted on him right now? Gravity. Great. So there's force due to gravity. Now, is this puck, just using common sense, is the puck going up or down? No. So there must therefore be, what prevents him from just plunging down into the center of the earth? Well, the ground, the floor, the ice, whatever's supporting it, right? So the force from the ice rink is exerting an equal and opposite force. Now, this is the tricky part. This is where you got to be, careful. Is there some force propelling him forward right now? No. If we tell his full life story, yes, 2 seconds ago, this dude exerted a force on him to get him up to speed. But 2 seconds later, at this point in time, there is no force required to keep him moving. There's Newton's first law is an object in motion will tend to just stay in motion. Basically what he was saying was we don't need anything there to say why the object is moving. It's just moving because it's moving. So anyway, that's the whole force diagram. And so the net force is 0, which means the acceleration is 0. What's the velocity, by the way? Is it 0? It's 20 meters per second.
Restriction.
Yeah. This was a bit of a red herring, right? Do we really need to know what speed he was launched at? Not really, no. So keep that in mind. You can have velocity, a non-zero velocity, while having no net force or acceleration. You just call that constant speed, constant velocity. All right. Are we still doing okay? Is it making sense? Okay. What are we doing for time here? Oh yeah, we can get to it. Sweet. I'm full circle here. All right. Number 5 says these next two should be pretty simple, hopefully. A 20 kilogram block is hanging from a cable at rest. Draw a force diagram and find the tension in the cable. So try to figure that out, see if you can get a reasonable answer, and then we'll go over the answer. Just go step by step. Picture him sitting there, draw a picture of it, and then go step by step. What forces must be present here? Here's step 1. He's a thing that has mass, so there must be gravity force exerted on him, right? And the formula is for how much force is gravity exerted is mg. His m was told to us, it's 20 kilograms. We know g on Earth is 9.8 meters per second squared. If I multiply those, I get 109, I think it's 196 watts. Newtons. So remember what a Newton is. That N stands for Newton. So a Newton is if you have a 1 kilogram object that's accelerating at 1 meter per second squared, that is 1 Newton. That's the definition of a Newton. Okay. More simply, it's just if you're doing a problem, this is, again, the beauty of like SI units in physics is if you just, at the beginning of the problem, if you just make sure that all your masses are in kilograms, all your distance measurements are in meters, all your time measurements are in seconds, then it will all work out every time. Then you'll just get newtons. You won't have to worry too much. So, okay, well, this would be a projectile. So what must be canceling that out? The force due to tension. Now, there's no formula for tension. Well, there are out there some probably, but they're incredibly complicated. What we can do, though, is we can infer that because the thing's not accelerating, because the acceleration is 0, there must be a net force of 0, which means this tension must be 196. So that's usually how we figure that kind of stuff out, is we say, I know how much gravity force there must be, and then, so therefore, this must be 196. Then in practice, now in real life, a lot of times you have an object and you're like, how much does this thing weigh? How much mass does this thing have? I don't know. So you calibrate a spring using a known weight, and then you kind of can figure out this number, and then you can use that to figure out how much this thing weighs. We'll get into springs later. Huh? Right, so scale is the same thing. Most scales are spring-based. You'll have a spring, and it'll say, how much did that spring compress or contract when we put the weight on it? Well, we know how much it would compress or contract when we put this 1 kilogram weight on it. So then you can infer what the weight of your second object was. All right, how about 6? Can I have a gravity vector pointing down, and could I have 2 forces pulling up? Sure, what's to stop me from that? Right? There can be 2 forces. You can have a ton of forces on here. Okay. So let's call this force from tension. Now here's where you get to be clever. You have to use some symmetry ideas. I hope you'd all agree with me. Those have to be the same size, right? If one was pulling harder than the other, the thing would get twisted, right? So just we will do some problems later on where the strings are at weird angles and then the tensions won't be the same. But if they're both if it's a perfectly symmetrical system, then there's no reason why they shouldn't be the same. So now what you can do is you can say, we know how to calculate, how heavy is this block for number 6? 100 kilograms. So that's 980 newtons. And so what I could say is that the force, this vector plus this vector has to equal 980, which means that each one has to be half of that. That should hopefully agree with your common sense, right? That they're sharing the load. Okay. Cool beans? All right. Which of course, this is one example of why it's easier to carry a table with 2 people than with 1, because you both take half the force if you're balancing it symmetrically. All right. For these calculation questions, there's a decent number of them. But the nice thing is they all follow the exact, there's one formula you got to know. Other than you might occasionally have to throw in some kinematics. Like if you know the acceleration, you can say, for example, figure out the final speed using kinematics. But remember our big, this is the big formula. Probably the biggest one of the year. F net equals Mn. So the net force on the object or system is just equal to the mass times the acceleration. So for number 7, number 7 says that there is a 50 kilogram block. Hopefully, I'm going to do 7 and 8. It's kind of important we can cover both. Okay, yeah, okay. You know, we got enough time actually. I'd like you guys to try to set up 7 and 8 on your own. 7, watch out for the 8's actually easier, believe it or not. Just try to set them up, and then we'll, in like 2 or 3 minutes, we'll talk about them. Is that the air conditioner thing?
Yeah.
Oh my God. So, hopefully you've had time to put some thought into at least read them. Did anyone draw a before and after, maybe? Especially if you were maybe slightly confused by it, a before and after would be a nice way to think about it, right? So let's say before, this 50 kilogram block was just chilling, right? So there was 490 newtons pulling them down. Everyone's cool with that, right? How much was the table pushing up? 490. So does everyone understand this? You sure? Okay. So the force from the table was 490. This is the before picture, before Bob steps in. Bob steps in, and Bob pulls up with 300 newtons of force, right? Do you guys think that's enough to lift the block? No. He would need at least 490 newtons to lift the block. So, but wait a second. This force diagram doesn't make sense because this would mean that the net force is down and the block accelerating downward. That's crazy, right? So how much force is still being pushed out by the table?
490.
Well, if I put a 490 there, oh, 190. Okay, so the force from the table would have to be 190 newtons.
Oh.
How do we feel about this? So what's the net force? 0. What's the acceleration?
0.
Does that agree with our common sense about the situation?
Yeah.
So if I have a really heavy block on the table, and you all have probably done this at some point, you kind of like you're putting some lifting force on it, but you're not actually picking it up. But what that does is it kind of alleviates some of the force that the table has to exert to keep it at rest. So are we all cool with that? So the sequence of thoughts here goes, well, firstly, 300 is not enough to lift the block. So it's not moving. And your mind might jump to this. I know net force has to be 0. And then therefore, what does the table force have to be in order to have this be happening? You cool with that? Okay, so that was the before and after. Let's do it for 8. This is a little bit easier actually. Because before, well, what is 9.8 times? $784. So in this scenario, I go mg, so 80 times 9.8. Okay. And then Bob exerts 600 newtons. Is that enough to lift the block? Okay, so what's up? Oh, you had a question, sorry. Okay, so you get the idea, hopefully. Right? These are both just net force being 0 problems. Make sense? So, by the way, this could be on a scale, for example. I'll show you this tomorrow. I'll get a scale and I'll show you if I put a weight on it and I pull up on the weight a little bit, it's going to reduce the amount of force the scale has to provide. So, last thing of the day, guys. So, by the way, how much force is the table exerting? 184 is the force. Make sure you label your diagram correct. Is it still Bob? Bob. Love you, Bob. So a good force diagram tells the reader where the forces are coming from. Okay, this force comes from gravity. Oh, it is on a scale. Sorry, I misread my own question. Yeah, it is on a scale. So this is actually, the force from the scale. And that's what scales do. A scale tells you how much force do I have to push on this thing to keep it to keep it up. When you step on a bathroom scale, that's what it's telling you. It's saying, hey, I got to put this many pounds of force to hold you up. Basically, that's what it's telling. All right, very last thing of the day, guys. Number 9 is very simple. You ready? You've got a 40 kilogram block on a table. And we push it to the right with a force of 80 newtons. Is that the full force diagram? If you want to be technical.
No.
No, because ostensibly this is happening on Earth. So there's going to be, these arrows aren't to scale, but there's the force from gravity, there's the force from the table. But these things cancel out. So do you have to really put much thought into those? You put them on your diagram to be complete and thorough. Also, in case something changes, maybe one of these numbers changes at some point in the problem. You gotta be aware of that. So anyway, who thinks you know the answer to what the acceleration is?
No, it's times 120. No, 300. But massive.
Okay, all right, so it's okay. So the formula says F net.
So you just.
Hold on, bear with me for 2 seconds.
You just do
F net equals ma. What's the net force? 80. What's the mass? 40. What's the acceleration? 2. 2 what? Meters per second squared. You guys are gonna like these problems. The math is extremely simple.
What's this first level?
What?
For 8, what will the scale be?
184. I'm sorry, I made a mistake. I was saying table. I should have been saying scale. But it's the same principle.
Yeah.
The scale is like a table that tells you how much force he's exerting. All right, guys, we'll continue tomorrow. Knock out a couple of these calculation questions. Do like 5 of them. They'll take you like 2 minutes each.